10 years ago, I didn't think that an AI model would replace a traditional numerical model. 5 years ago, it started to become clear that that was the case.
You seem to me very passionate, obviously very accomplished. What is it that you think about that's stressful?
The thing that I have found challenging, and I think many people have found challenging, but also exciting, is how fast this field is moving.
If I understand correctly, you actually put a model in orbit.
Correct. This is one of the coolest things that's happened very recently.
AI is an incredible tool for small change. For me, it solves problems daily, like writing emails or managing my time or researching something I have no idea how to do. But it also can be an unlock for huge, and I mean huge, scientific questions. Today, we're joined by Campbell Watson, an IBMer who is on the forefront of using AI to solve massive geospatial problems. Campbell, welcome to AI in Action.
Great to be here. Thanks for inviting me.
So I know you're a surfer. I read your bio. And I'm actually really curious of how you got to this point of the intersection of AI and earth science and now space science. Like, what originally motivated you to work in this domain?
I think wearing a suit as a 21-year-old going to the 35th floor of a city building in Melbourne as an accountant. That's what drove me here. So I started out as an accountant. That was my degree. I was doing tax returns for very rich families and especially their children. And I was surfing as well and realized that's really where my passion is. So I went back to school and learned earth science, a lot of physics, a lot of applied math, and really focused on ocean and earth science. And that just evolved into a lifetime of learning.
So it was the surfing, was it that connection to just being in the water and being with nature? You're like, I can't deal with this suit and accounting. I need to really focus more on the earth.
I think so. At the time, I had little appreciation for the structure of finance and the role it plays. I have an increasing appreciation for it now as I've got older. But at the time, I was interested in the world around us and being able to study how the ocean circulation, how the ocean moves around the planet, the interaction of fresh water and salt water, how clouds form, why it rains more over mountains, and the very specific physical processes that occur in clouds. This is what really grabbed my attention.
So how'd you get into AI then?
I started with what we call numerical methods.
Okay.
So my PhD and then my postdoc that I did at Yale, this is one of the reasons I moved to the US, was on cloud physics. Actually, funny story is that my first business card that I ever created was a picture of a cloud with a question mark in it because I was a cloud scientist. And then IBM Research had this opening for somebody that knew about ecosystems and could do modeling of those ecosystems, which I applied for and got. And then suddenly my business card had a totally different meaning, being IBM investing in hybrid cloud. The original focus of that work at IBM Research was numerical methods. So using, the way weather models are traditionally run using large high-performance computing environments and crunching mathematical equations or partial differential equations over and over and over again. There were certain limitations that I encountered with this method, and the community did in general, the research community, especially in the field of hydrology. And so this is stream flow, so how much water is moving down a river where there's sparse observations. And we found that machine learning was a really great way of approximating water flow through systems like this. And so seeing others at the forefront of this research in the community start to tackle stream flow and hydrology with machine learning models really motivated me to learn about it. This is in about 2016. And that was the beginning of my journey into AI.
Was this like a totally novel? You saw this happening. You saw large language models, foundation models. Did you, when you heard about this technology coming to the forefront, did you expect that it would be a boon for your particular field?
10 years ago, I didn't think that an AI model would replace a traditional numerical model. 5 years ago, it started to become clear that that was the case. That said, they will exist together. And I think that's what the interesting thing is for computational scientists to figure out today. How does traditional computing, CPUs, AI, GPUs, and quantum, qubits, how do these fit together for the type of computational problems we want to solve together in the future?
You're looking forward ahead to quantum computing now, also in the same field.
Oh, absolutely. That is something that we're thinking about for the next 5 years.
And you're in Yorktown. I know I spoke to you before. You work at IBM's research facility in Yorktown. And so you have access, hypothetically, to a quantum computer. Were you able to do any fun work with it yet?
So we have, there's obviously a lot of quantum researchers in Yorktown, and we work very closely with them on defining what it is we should be working on together. So right now is a really exciting time within research as we tackle this big computational problem.
That must be so much fun. I was saying to you before, like I work in tech sales. It's very fun, very rewarding. I love my job, but sitting around in a room with all these brilliant people, and especially because you're working now from machine learning to large language models and now towards quantum computing, you're sitting around with all, did you just bring them in? You're like, hey, listen, I know you work with quantum computers. Can we have a conversation? What do you think? Is that how it happened?
I think it was a little more organic than that. Particular problems emerge in a domain, and we think, hey, it could be answered with this. What I've found, just for my personal and career growth at IBM, is that I've had to get over intimidation, right? I can sit in a room with quantum scientists. The mathematical notation they use is not the mathematical notation I use. And so I can very quickly become confused and lost and intimidated. And what I've learned is just by having confidence to ask the right questions, we can begin to speak a common language. This also requires diligence on my behalf and their behalf so that we understand the technical grounding, the technical background we each have and the problem we're trying to solve together. But I think you'll see at IBM Research over the coming year, this is a much more common pattern that I'm interested, and our group are interested in Earth and space. We work closely with NASA, as I'm sure we'll talk about. And we think about what are the computational problems in Earth and space, in the Earth and space domain, and how can traditional computing, CPUs, GPUs, and quantum work together to help solve these problems.
Can you talk a little bit about how you got over the intimidation?
People are open, people are willing to share, and interest and curiosity can really get you a long way. When I started at IBM Research, I came in as a cloud physicist, like the physical environment, and then I was suddenly working with platform architects and computer scientists. I knew nothing about these disciplines in a formal, from a formal perspective. And it's through experience of working with them and realizing what we can achieve when working together that I have confidence that charting a path like this, empowering others in my team to also do this, is a way in which we can achieve really great things.
It's something I noticed in the community in large. Like I know that we can talk a little bit about open source, and it's something I was talking to some of the people here about, just the way people are open to sharing their work, and that allows us the opportunity to learn about things we wouldn't know. So for example, I know that you trained a foundation model, and I knew nothing about, it's all abstracted for me. I'm like, at my level, I'm utilizing the models to do something functional with them, like in agents or whatever. But there's this guy, his name is Andrea Karpathy. He released a GitHub repo that I recommend everyone look at. It's called NanoChat. And seeing how he explained first how the transformers and decoders and all this stuff works, and then how you train the model itself to get to like a GPT. It allows an inside view that I think is very unique to our field.
The last 5 years especially has been incredible for open source AI. I think there's been a few driving factors as to why there's so much emphasis on open source. And our team have really been beneficiaries of it. We are scientists for the most part. We're interested in doing open science, sharing that science with the community, believing that the community can then provide back to us. We can work together. We can create something better that then we translate into value for IBM. So we're not doing this alone. And we work closely with government agencies. NASA is one of our primary partners, who also have an open science, open source policy. And so the last 5 years, we've seen the work that we've been able to do in partnership with NASA, the European Space Agency, ends up in the community's hands. And it's incredible when we run a virtual workshop and 300 people join who all open up Python notebooks, download the model from Hugging Face, clone the repo from GitHub, and then they start playing with our model there in that 2-hour workshop. And these are people from all over the world. And this is the beautiful thing about it. You're seeing the papers get subsequently published using our technology that we've built.
For myself, when do these workshops happen?
We try to do it in collaboration with other organizations. The UN is an example in Europe, and we often do them with NASA as well. But I will add you to the mailing list.
Please, seriously, please add. That sounds so fascinating. So you mentioned you work with government agencies, NASA and the European Space Agency. How did these collaborations start?
They started from a shared curiosity in how AI and this large language modeling paradigm can help Earth and space science, and especially all the data that's being collected. Some of our early conversations with the group at NASA were around, we have these very high value data sets that we're collecting. This is from NASA's perspective. Their domain scientists are building their own models, building their own tools to analyze this data. We want to unify that. We want to unify it in a way that's very open and transparent and usable by a broad section, so that when the experts come in, they can add on top of this layer their own expertise. The idea of a foundation model, so a model that learns from a given data set or a group of data sets, the representations, information that's in that data, seemed like a really nice fit. This is what large language models do. They learn from a huge amount of written language. And so we set about building a foundation model that knew about satellite data. And there's this wonderful data set that NASA have collected called the Harmonized Landsat Sentinel-2 data set. These are 2 satellites operated by NASA and the European Space Agency that measure multispectral optical imagery. And so we have global coverage every 2 to 3 days from these 2 satellites. They've downloaded them, unified them, or harmonized them, processed them, so they're very user-friendly now. And we trained a foundation model so that it kind of knew things about this data. I guess when we started, we actually thought about it as a data science tool, so that a user could come along, take our foundation model, and then do data science. And the foundation model would give them a head start. They wouldn't be learning from scratch because they have a model that already knew things about satellite imagery. I sometimes think about, you look from space and you see the ocean, and then you see an algal bloom emerging from a river. We would probably know there's something in the water, right? It's sediment, it's an algal bloom, it's something like that, right?
You would know that. I wouldn't, but go ahead.
But if you were to start training a model from scratch, that model, of course, doesn't know that. It just knows that it's suddenly a different color, if it has a sense of color, which if you use RGB, it does. The foundation model already has a sense of these 2 things being different, that there is an area in which something has changed. And so then we can adapt that model, we call it fine-tuning, to detect algal bloom formation, as an example, or detect deforestation where that's occurred, or when floods are occurring in real time.
My understanding of foundation models are large language models. So I think of the way that I interact with the model is I send natural language to that model to get a response. Mm-hmm. For your foundation model, what is how do you interact with it? Is it natural language? What are you sending to the model to get anything back? Is it images? Is it what is the data type that goes into that model for you to get a response?
Primarily images. So we feed in images and we get out images. The way the models are constructed, the foundation model itself, is through unsupervised learning, which we call masked reconstruction. And so we provide the model a satellite image, and then we black out parts of it, and then we ask the model to just reconstruct the blacked out parts, the missing pixels. And you do that over and over and over and over and over again. And we can keep on doing that because we have a lot of satellite imagery. Then through that process, the model starts to learn what a satellite image should look like. This foundation model is really good at reconstructing missing information. That doesn't mean it's really good at telling me the height of a tree or telling me if a building has been damaged. And so that's where the second step comes in, which we call fine-tuning. And this is where the user experience becomes really important. We have to provide examples of, here's a satellite image, and this is what I want you to tell me from this satellite image, the label. For example, here's a satellite image of the ocean with some ships. And then here is where the ships are located, would be just little circles around the ships. And then we can very quickly fine-tune the model so that in the future, when we pass in a satellite image, it'll tell us exactly where the ships are.
So what are you doing with this model that's going to blow everyone's mind?
We've worked on this for 3 or 4 years now with NASA and now the European Space Agency. We've learned a lot in that time. We've released 3 foundation models for satellite imagery, which we call Earth observation data, a foundation model for weather and climate, a foundation model for the sun, heliophysics. We're working on one for the moon as well.
Okay, so a foundation model for the sun. What are you looking at with the sun? Like spots? You're looking for, what is it called when
Solar flare?
Solar flare. Like, how do you know? Just by the hand motion?
Yeah, just the hand motion.
Just thinking. Like, so that's what you're training the model on?
We're training it on the underlying data.
Okay.
So just like I described with the satellite imagery, NASA have a satellite that's looking at the sun, and it is observing, again, in multiple bands, the sun at multiple depths, and we train a model to try to understand that data. And so it's doing a mixture of reconstruction and also forecasting. That's how it's being trained. So it can always predict what happens in the next step. Then we can fine tune it for a range of tasks. So one of them is, will a solar flare occur in the next 24 hours? That is a question. And, we say, what category solar flare will it be? We ask a question of, are there any active regions that are likely to develop in the next 5 days? What will the impact on space weather be with respect to satellite navigation? And so we can actually look at, have it predict deformations of the gravity field in space, which is really important for satellite navigation. Fascinatingly, satellites go missing all the time. They get found relatively quickly, but they do get moved from their orbit because of activity from the sun, and we lose track of exactly where they are.
Do you not have enough fuel to get back into the correct orbit? Like, what is that? What happens?
They often do, but they do shift from their orbit temporarily.
And then, so they're lost only for a little bit, but then they come back.
Only for a little bit.
Okay.
And also, if it's a large enough solar event, they will take protective action, satellites, and actually kind of cover themselves with a shield to protect themselves from the radiation.
I didn't know that, really. So
Yeah.
And now this model will help protect, what is the lifespan of the average satellite? I always thought that it's good forever.
No, not forever, unfortunately.
So this is ways to ensure that they are able to stay in orbit and function for longer.
Yes. It's good hygiene. So that's an example of the model that we've built for the sun.
That's amazing. I know you said when we walked in that you're like, well, I would like to know more about financial services. And honestly, it's very cool, but you have to recognize how cool this is, right? You do.
It's great. I mean, it's great. Couldn't be done without our partners.
Yes.
So when we kicked off this work, it was 2020. It was a decision that we should do something related to AI and climate. What should it be? So me and a colleague kind of created a technical roadmap, AI, climate impacts, and a few other things. At that point, we were missing a key partner, somebody that could really take our work to the next level. And then, we were fortunate enough to be connected with this team at NASA who had this vision of, we want to have these large AI models we can think of as data science platforms to help users use our data. And from there, we've sort of, it's been a fantastic journey. And with the European Space Agency, we've really been able to focus on what we call multimodality, which is another fascinating area of research.
So when you were coming up with your technical roadmap, NASA was doing something in parallel and you happened to just meet up at the right time? Or did NASA come to us first, or did you go to NASA first? How did this work?
NASA actually came to IBM to talk about exploring scientific literature. So it was a text problem.
Okay. and then you're
which is a project that has taken place and has been occurring in parallel to our group. And it was through that, it's relationships often start small. And it was this organic growth. Hey, what if we kind of take this paradigm and apply it to satellite imagery? This should work. It's a vision modeling. It's different to language modeling, but there's similar patterns involved here. And so that is where it started.
I feel like it goes back to what you said at the beginning of the podcast, where you're saying curiosity is what drives this innovation. I feel like both teams, IBM and NASA's team, were just both very curious about this new technology, and it's really a wonderful thing. So you mentioned multimodality. Can you go into that a little bit more?
when I've talked about satellite data so far, I've talked about optical imagery. So it's these nice pictures that you see from space of the beautiful blue Earth. There's all these other ways of sensing the planet. One of them is with radar imagery. You might see, remember, was it last year or the year before, there was a large earthquake in Turkey. And these images emerged that actually showed the displacement of the Earth by, in this case, I think it was several feet in certain parts. This is measured by what we call radar, which is just a totally different way of sensing the surface of the Earth. There's LiDAR. This is another way of sensing the Earth. The challenge is, well, we want to use all of these observations. So can we come up with an AI architecture that allows us to harmonize or unify all of these data modalities so we can use them together to squeeze the most we possibly can from everything that we're observing?
Is the pipeline always the same? Like, are you looking at radar, then putting the response of that into whatever other part of the foundation model, like, or the satellite imagery?
Good question. Yeah, a great question. We've explored so many different options. What we're focused on at the moment is what we call discretization. And so in essence, we know the data has a particular distribution, and we chop that distribution up in a clever way so that it goes from being an image into what we call a vector or a line of information. And then this can be more easily combined with the other discretized data modalities that we've processed. And so we call these tokenizers. So we have a tokenizer per data modality, which are then combined. And there's a correlation learned across each of these modalities or each of these sets of tokens.
So on top of all of this, if I understand correctly, you actually put a model in orbit.
Correct.
Okay.
This is one of the coolest things that's happened very recently.
Tell me about it, please.
This is the beauty of working with European Space Agency, NASA as well. I mean, with these fantastic government organizations. With the European Space Agency, we built TerraMind. Then we also built a small version of TerraMind. The models that we build, they're nothing like large language models, which are tens of billions of parameters and take data centers to run. The models we build are hundreds of millions of parameters.
Really?
You can generally run them on your laptop, but we actually built an even smaller version, one that could run on your iPhone, one that can run on a Raspberry Pi, could be deployed on a drone, one that can be deployed on a satellite in space. And this is what the European Space Agency enabled for us, working with an Italian space company, placing the TerraMind tiny model on a bit of hardware that is now orbiting the Earth.
And you're getting results?
Not yet.
Oh, not yet.
It's
okay.
just so recently launched. But the idea is that, so you have this foundation model. This is TerraMind Tiny, as we call it, which knows information about optical imagery, radar imagery, etc. And then when we want to adapt it to do a specific task, we add what's called a decoder head. And these can be very small. These can be 2 megabytes in size. It can be used for detecting floods, detecting deforestation, for identifying herds of animals, population movement, etc. If you can do it with satellite imagery, then you can do it with this model. The idea is that because it's just a 2 megabyte file that needs to be uploaded, the decoder head itself can be trained on the ground here, where we have access to GPUs, and then sent up to space and added to the model that's sitting on the satellite. Now the model can process data in space and only send back down the data that's important, the insights that are important. And so this is moving towards this paradigm, which we call software-defined satellites.
Where you're able to train a decoder on the ground and then update its capabilities from the ground by just uploading it to the satellite?
That's what we're going to be doing next year.
I have a question about the decoder a little bit, and a little bit naive. I told you I was going through Andre Karpathy's YouTube series and his GitHub repo, and he was really going through the decoder encoder. And obviously, very simply, he trained it on Shakespeare, and then he said, okay, to be or not, and then he showed the mathematical representation of it, which is, how does it work in this case, the 2 megabyte decoder? How does that actually look? Like, is it still just matrices of numbers, and is it the same thing?
Yeah, it's a model architecture, so it's neurons and then it's weights that go along with it. I mean, it's 2 megabytes, it's tiny. It's a limited number of parameters that can translate information that comes from an encoder, which is the foundation model. So the encoder creates what we call this latent representation of the satellite imagery. And then it gets interpreted or translated in some way into something that we're interested in. And so if we're interested in tracking active wildfires, it would be a segmentation model that will detect, here is a wildfire, and this is the very particular region it's located. And then it would just send back a very simple 2-color map, for example, or a blank map just with a circle of this is where the fire is, which would be a very small file.
Let's look back a little bit. Developing the geospatial foundation models themselves, putting them into space, making them accessible to non-experts across the industry, which was harder? Like, what was the hardest part of all of this?
Great question. Both are important, obviously. And it's something that we can't do by ourselves. I think building the technology, yes. We're confident that we can build the technology. Doesn't mean it's easy. But we have built the technology. We've open sourced the technology. It's called TerraStack AI. If anybody's interested, this is the technology for running these models, now open source. Making it get picked up and easily usable by others, this is where we really rely on the community. We, of course, we have good hygiene when it comes to software development. I know we're researchers for the most part, but we're also trained software developers. So the code that we release is good quality. Working with NASA, working with the European Space Agency, working with other companies and government organizations, we're able to get this technology into their hands and then work with them to help them answer their questions. It's all about enablement. Every now and again, we'll be talking to a community, to a group of users who don't have the skills required to work on this, to work with the models. This becomes challenging. And, you know, we will try to find ways to help them skill up so that they can use it, put them in contact with relevant groups. But our core mission is to build the technology, to do the science, to do the research, build the technology, and do it with great partners that allow us to have the largest amount of impact.
Do you think there's any intention in the future, maybe to make this enablement? Because this podcast is going to go out, people are going to obviously want to do this. And I know that you've worked with other organizations to do the workshops. Is there ever an intention to make it wider, like have a wider audience where anyone can just join a workshop on YouTube or go to a GitHub repo?
So the workshops that we do are generally completely open, but you need to know about them. This is, you know, it's still a somewhat niche domain. We're talking about analyzing satellite imagery, or soon it will be exploring things on the moon. It's not everybody that wants to use it, but you know, it's all on GitHub. There's instructions on how to use it. The models are uploaded to Hugging Face. So we do what we can in terms of documentation and usability. We have Slack channels and Discord groups where interested parties can come ask questions, speak to the developers themselves. They can, reach out directly to us. So the support is there. Our interest is in, what do the next 5 years look like in terms of computation?
To go back to, you said the foundation models you have are relatively small. Was that like a purposeful decision, any environmental like thinking about like the energy use of the GPUs, or was that a purposeful decision? Because you could have, I'm assuming, had a tremendous model, but you didn't need to, or was it never a necessity to have a big model?
The motivation, honestly, I don't think was driven by energy consumption. It was driven by usability. So most of the users of our models are other scientists, researchers, developers, and enterprise users. But when I talk about enterprise users, it's often the R&D groups of, large companies. They don't necessarily have access to large GPU clusters in which they can fine-tune the model. They might have a couple of GPUs. And so we want to make sure that the model is usable for them. And so that's why we've limited the size of these models. We could have built a 10 billion parameter foundation model for working with this information, but then who would use it? We would have learned things doing it, and if that was our motivation at that time, that would have been justified. But in our case, we wanted to make sure that it would have as much reach as possible, and it's something that I think we've been very successful at.
So you thought about the foundation model. It was always with the intention of having it fine-tuned?
Yes.
Okay, why?
Because the foundation model itself, it's good at reconstruction. So reconstructing missing information from an image, or it might be good at predicting the next step of a system in the case of weather. But that is only a fraction of use cases. There's all these other use cases. So we want it to be task agnostic, as we call it. And so fine-tuning is really important. Where I think we are moving to, and will become more apparent next year, is actually moving away from fine-tuning, because the information that's in the latent space is enough to do the tasks you're interested in. So you can do few shot or zero shot or few shot learning with this type of information, which I think will be really cool. And this is actually moving towards this world model paradigm that you might have been hearing about.
So for the quantum future, right, the stuff that we're talking about, the computational power of quantum computing, it could decrypt all of our encryption, which is very scary. What about unlocking science in Earth and space? What can it do there?
We have two areas that we're focused on in terms of quantum. One of them is dynamical systems, so partial differential equations. When we look at Mars, the Martian atmosphere, we know it exists. We can see the dust moving around. We have a couple of satellites that are observing it, but it's still pretty sparsely observed. We have two rovers on the ground. So we have these single points and some cameras. So we know the atmosphere exists. We can tell that it obeys, the physical laws that we would expect, which are kind of derived from, which are Navier-Stokes based. There's complications around radiation effects because of the dust. How do we create a model that can best represent and ultimately make forecasts of the Martian atmosphere? We're thinking about coming back to partial differential equations themselves. How is it that AI can help us solve these equations faster, especially when we have sparse information, such like we do with Mars? And what about quantum? There's quantum PDE solvers that are being proposed and will soon be tested. And so ultimately thinking about, it's a computational problem. How is it that we can use these different modes of computation to solve a problem like reconstructing or forecasting the Martian atmosphere?
And is that just due to limited data? Like, is that when you look at this use case for quantum, you're saying, okay, we don't have enough data to really forecast the Mars atmosphere?
Yeah, with quantum, it's not necessarily an issue of sparse data, not necessarily specific to Mars, but it's an example where bringing it back to the partial differential equations themselves, as opposed to just training a model based on the data that's available, which is what the AI weather models are these days. They're models that are trained on available data. We think that by focusing on the PDEs themselves, we can translate it more easily to quantum.
So have you seen any applications that really highlight the power of these foundation models? Like somebody took what IBM and NASA and the European Space Agency have provided in these foundation models and used it to make something particularly cool. Have you seen anything?
The coolest one I think we covered already, which is putting it in space.
Yes.
I mean,
okay.
That's incredible. I can't wait to see what people use it for. I believe it's going to be opened up to universities across Europe for people to be able to upload their own decoders. A nice example that we put together recently was actually fine-tuning the model for detecting elephants across parts of Africa. I think this is a really feel-good story.
Yeah.
This is one. Another one is we've had a really great research partnership with Goldman Sachs recently, looking at biodiversity impact assessments. And how is it that multimodal AI systems and foundation models can speed that up? And we've focused on this area in southern Chile called Caraquinca Natural Park, where peatlands are in decline. And so trying to observe them from space and see how they change, how they're impacted by fires, how they're impacted by land use change from agriculture and similar. That has been a really enjoyable and scientifically interesting challenge to work on. And especially, working with Goldman Sachs, it's been a real lesson for me in what it is, how to translate the science and research we do into something that is useful for an industry like that.
And you would hope that the result of, looking at the biodiversity, you're saying that there is negative effects to the environment, that the resulting data that you get might actually impact change within society. That's one of the big things.
Can guide financial investment decisions.
So for organizations exploring AI for sustainability, what's one piece of advice you'd give them?
It really depends at what point of the AI journey they're on and how it is that they want to address sustainability. IBM acquired Invisi, a carbon accounting company, maybe about 3 years ago. They're a sustainability company. And so we actually work closely with them, bringing large language model capabilities into their product. They had almost nothing that was, driven by AI or AI enhanced or whatever you want to call it. And so that has been a really interesting process for us. We understand large language models, how to adapt them to specific tasks, but then this is sustainability. It has regulations, it has policies, and then it obviously Invisi has users, and they have products that they want this to feed into. Ensuring that what we build meets these three criteria has been a challenging but very rewarding journey. It's taken a lot of working together to define all of this. So what I would say, just generally about AI is, if you're thinking to bring in a new AI capability, make sure it's going to be useful. Understand what it's going to bring, and then that it will add value to what you're already doing. I know that's a very kind of generic answer.
It is, but it's true, right? It's generic because it's true. I wanted to ask you before we started, you said that you'd wake up in the morning and think about work, and you want to try to not think about work the second you wake up. What are you thinking about when you wake up? What was it that you were thinking about? You seem to me very passionate. You seem obviously very accomplished. Like, obviously, I am assuming that you don't want to think about work because it's a little bit stressful. I mean, that's what I wake up in the morning, I think about work. But what is it that you think about that's stressful?
The thing that I have found challenging, and I think many people have found challenging, but also exciting, is how fast this field is moving. This is something that keeps me up at night, how fast we're moving and how quickly we can adapt to the new things that come out. Our group, we adapted really quickly when the first large language models emerged and totally changed the landscape. And this is quite hard in research, right? In research, you often have projects that have 1, 2, 3, or 5 year timelines and roadmaps. But we very quickly recognized this is a transformative moment, as a lot of people did. And that is when we ended up with a great partnership with NASA. This is the thing that keeps me up at night, not becoming complacent with what we've got and making sure that we're staying ahead of the curve.
Flexibility.
Yeah, flexibility and strategy. These things keep me up at night.
When you said you pivoted quickly, was it based? What's the name of that paper? The famous paper about transformer model.
Attention is all you need.
Yes.
See, that was 2018. That was well before any of this.
Okay, so it was before. So it was, what was it? Was it seeing GPT?
Yeah.
Like, it was the first time you saw GPT. And that was crazy.
That's right. So we used transformers in earlier work in 2020, and we had some nice results, but they weren't transformative. It was this notion of doing large scale pre-training that really changed everything for us.
Is there one problem that you want to research where the technology is not there yet? Is there something that comes to right to your mind? Like, the technology is not there yet, but I need to understand this.
My mind is always going back to clouds because this is what I started in. I would love to better represent the processes that are occurring in clouds.
Campbell, honestly, thank you so much. This has been so fascinating. This has been the most rewarding conversation I've had in a very long time, and I really appreciate you spending time with me today.
Yeah, my pleasure. It's been great.
And thank you all for watching and listening. We'll see you soon.